Okay, so I'm going to talk to you about the Origin Space Telescope, which goes from 5 to 660 microns. And we'll be probing from first stars to life. Those are the science goals. For those of you doing our scavenger hunt, the secret word for this presentation is decadal studies, and that's the URL on how to do the online form. All right, so Origin Space Telescope is sort of driven by three main science areas. One of them is seeing into the dark ages. So we all know and love Hubble. Hubble's given us all sorts of information about galaxy evolution out to sort of the point of reionization. And James Webb, which will be launching in about a year or so, is going to sort of pick up from there, cover all of that, and take us up to the first galaxies. But to really understand this complete picture of galaxy evolution, you're going to need something like Origin Space Telescope that seeks back in towards the dark ages when the galaxies actually form. And so some of the core science themes in the extragalactic realm for Origin Space Telescope is to look at when and how the first galaxies formed, and then to look at their evolution, look at the rise of dust and metals over cosmic time, and then to look at the coevolution of galaxies and black holes from when they started forming to the present day. Now to do that, to get that sensitive, things are redshifted, so this is optical, infrared. So we start where Webb is, we start where the mid-infrared is, and then we go out to the far infrared, so you can actually cover the whole of the cosmic history of the galaxies. That's why we go from 5 to 660 microns. Now to operate an observatory like that, you need to make it big and cold. We're doing two concepts. At this AAS meeting, we're talking mostly about concept 1, which is a 9.1 meter aperture, cold to 4 Kelvin. And I'll get on to the next science theme. This slide and the next series of slides is sort of showing our two other main science themes. So one of the cool things I like about Origin Space Telescope is we're going to get the whole story of how habitable planetary systems form, and then to look for life on nearby habitable planets around M dwarfs. So following the formation of planetary systems in the ingredients from the interstellar medium to life-bearing worlds is one of the themes, but it's really sort of two separate key science cases. So one of the key ingredients that everyone thinks are important to life is water. And the transitions for water basically exist in the mid-infrared out to the far infrared. So if you want to follow the trail of water, which we all understand is important for supporting life as we know it, Origin Space Telescope gives you that story. So we start in the interstellar medium, and then we can follow the water and also other sort of organic materials by studying spectroscopically and also with the dust, protoplanetary disks. And then we can follow these disks to the point where they're actually in the process of forming planets. So they have sort of less gas and dust, but Origins will be sensitive enough to actually pick up both the gas and the dust. And so one of the goals of Origins is to measure the gas mass of over 1,000 protoplanetary disks where they're actually forming planets. Right now we have sort of a handful of those from Herschel. But we're expecting with the sensitivity increase with OST that we'll be able to look at 1,000 of those. So that's giving you real statistics. It's really giving you a good idea of how these systems form and what materials actually go in there. And then you can also study through the mid-infrared spectroscopy, which gives you the water ice. You can understand where the snow line is, where is it icy, where would it be liquid. And then the final leg of this is to, again, look at exoplanets. So one of the reasons we renamed ourselves from Far Infrared Surveyor to Origin Space Telescope is that we extended our wavelength down to 5 microns in order to support exoplanet science, beyond just looking at the formation of planetary systems. And our exoplanet team has been looking at ways to basically make a specialized transit channel that is high precision in terms of sensitivity to get down the noise in the transit so we can actually detect the biosignatures. And I'm thankful that Habex and Louvre defined those for me because I don't have a plot, but basically methane and ozone and water, nitrous oxides all exist in the mid-infrared, and we can get that all simultaneously, so you get a complete picture of what is going on in the atmospheres of these planets. So I want to end by talking about the discovery space. So as all these other decadal missions, we're defining the capabilities of the observatory based and trying to hone the instruments to definitely support these key science cases. But there's a huge amount of discovery space in Origin Space Telescope. So on the left, we show spectral line sensitivity. So this is 5 sigma and 1 R sensitivity versus wavelength. So this is 5. This goes to 1,000 because we wanted to show ALMA. And the prior space missions, Herschel-PAX, Herschel-Spire, Sophia PPLS, and this is JWST MIRI, are shown here. And then Origin Space Telescope, the reach is to basically get up to 4 orders of magnitude increased sensitivity. And it's this increased sensitivity that's going to actually let us probe all these nearby protoplanetary disks. This MRSS is the medium resolution survey spectrometer, and it's going to be doing the deep extragalactic fields. It'll be able to go sensitive to pick up those galaxies, millions of galaxies, over cosmic time from nearby to far away. This is the HERO spectrograph. Its resolution is the highest that we have, and it's going to allow kinematic studies of the protoplanetary disks and also turbulence in the interstellar medium. And then, of course, this is MIST. MIST is a mid-infrared imaging spectrometer coronagraph. And one of the spectrometers, as you can see here, there's sort of 3 resolutions for the spectrometer for MIST. Imager, medium resolution. One of these is the specialized transit channel. And then we have the sort of medium resolution you might use for extragalactic, and then sort of the high resolution for metallicity studies. So we're hoping to hear from you all, and do you want to learn more? You can come over there and talk to us. Do you want to participate? Look at our websites, or go to, this Goddard website tells you how to kind of plug into our telecons. But using that discovery space, we would love to hear what sort of ideas you have to do with this observatory in the next decade. And again, the scavenger hunt keyword is decadal studies. And I also want to, we have 1,000 of these. And so I'm hoping that people will take 1 or 2 home, give to their children, grandchildren, high school students. Anyway, thanks for your attention.